Hello everyone, welcome to Hudson Engineering Academy. It's me, your tutor Hudson, and today I'm pre-stressed concrete. So please, before I continue, do subscribe to my channel, hit the notification bell so that you don't miss any of my video. Whenever I upload a new video, you get notified. Well, in our question for today, the question says, an unsymmetrical I-section beam is used to support an imposed load of 2 kN over a span of 8 meter. The sectional details of the beams are given. The width of the top flange is given to be 300 mm. Thickness of that top flange is given to be 60 mm. Thickness of the web is 80 mm. The overall depth of the beam is 400 mm. At the center of the span, effective prestressing force of 100 kN is located at a distance 50 mm from the soft pit of the beam. That means from the bottom of the what? Of the beam. Now here our question says we have to estimate the stresses at the center of the span section of the beam for the following loading conditions. The first condition is prestressed plus self-weight, and then prestressed plus self-weight and live load. So the first one, it will be on a dead load, which is the self-weight. Then the second one, we have to bring in the concept of the live load inclusive. So let's look at how can we calculate this problem. First of all, diagrammatically, let's have it this way. This is the I section and all the details provided. This is 360, 80, 160, the overall span being 400. That's what the question says. Now, according to this question, and this is the I section, the first thing we should think of is to find what could be the centroidal distance from either top or bottom. This is to find the centroid. So in our first solution, we're working on that. First step, the centroidal distance from the top. And this is given by expression as you learned in your mechanics. So centroid y is given by a1x1 plus a2x2 plus a3x3 plus divide by a1 plus a2 plus a3. Now what am I saying is x1, x2, x3, you need to know. So the area, I'm calling the upper figure, the top flange as first area, A1. Okay? So the area of this one is 300 times 60. Then what I'm calling x1 is what is the centroid of that very figure, that top flange, the centroid. You find that half of 60 is 30. That's why we are multiplying this by what? By 30. Okay? So you do the same. Now, the second part, this web. So the distance, the overall distance is what? 400. So that means this web is 400 minus 60 minus 60. You remain with 280. Okay? So if that is 280, that's why we are having here what? 280 times 80. So that is the what? The area. Then what about the centroidal, the distance, the centroidal distance, but from the top? Okay? So if I divide this 280 by 2 is 140. So that means at half of this, from here to here, is what? Is 140. So if that is the case, 140, then plus this 60, it becomes 200. So that is what we're calling the centroidal distance from the top for the web. Now that is done. That's why we have here what? 200. Then 100 times 60 for the what? For the bottom flange. So that means we multiply it with the what? With 370. From the top, half of 60 is 30. So 30 up to here. 30 plus 280, then plus 60. So you come to 370. Then divide by the area. The answer is coming to 156. This is our centroid. In detail, this is our what? Figure. Now I've added where we have the neutral axis from the top up to this center, where we have this neutral axis or the centroid, it's 156. That's the value of y that we got. That means if you deduct it from 400, you get what? 244. That's why we have 244. And as I told you, here is 280, and half of this 280 is 140. Okay. Now the question says it is located. What is located? Let me bring back this question, and you see the question says a force of 100 kilonewton, prestressing force, is located at 50 mm from the soft pit, from the bottom. Okay, so from the bottom is here, the force of 100 kilonewton, let's say it's here, 100 kilonewton, is located at that very point, leaving an eccentricity of from this part up to this part, where from here up to here is 240. Okay, so when we subtract 50, we remain with eccentricity of 194. As easy as that. So that is how I've shown you here. I've given you that the total minus 156, that is to give you 244. Then minus the 50 at the bottom, that will give you 194 as the what? As the eccentricity. Okay. Now, next is, let's have a look at how can we calculate the moment of inertia of this particular I section. I. Okay. Now, this is what I'm calling the procedure that you need to follow to calculate moment of inertia. The formula says B1 H1 cubed by 12 plus A1 R1. Then you apply to each figure. You just change to figure 1, figure 2, figure 3. That's when you consider flange, web, flange as different figures. Okay? Now, the question is, if I know all these dimensions, do I know how to take what is B1, what is H1, what is A1, what is R1? That's the most important thing, and I believe this we learned in mechanics. But a recap of it so that you can understand very well. So how to find I. Now, this is the figure. Starting with considering this as first figure, second figure, and this one is our third figure. Okay? If that is the case, what is my B1 and what is my H1? My B1 is the width, the breadth. Okay? So this is 300. And then my H is what? 60. So that's why I've written 300 then times 60 cubed divided by 12. And then plus area of the first figure, 300 by 60, as you can see. Okay? And then we multiply with R1. A big question. How do we get R1 and what is R1? Now, we realize that this figure, since we have divided each of them, the centroid of this one, of this first figure, is different from the centroid of the overall section. You get it? So, the R1 that we're talking of becomes what we call the centroid, the overall centroid, which is from here up to down here, minus the centroid of what? This one, when you're considering from the top. Okay, so if that is the case, that means my R1 is going to be 156, because that is the centroid from the top, minus centroid of this figure 1, which is 30. This is what we're calling R1, and it's supposed to be what? Squared. So that's why I have here 156 minus 30 squared. Apply the same in the second what? Figure. Now we realize that the second figure is the web, and the area is 280 times 80. Thickness is 80. Now what is the breadth here? What is the width here? And what is the what? H here. Here is where you will easily get confused if you don't follow it carefully, because people think that what is long is supposed to be what? The breadth, which is not the case in this. Okay, so what is horizontally, which is what? This 80. Treat it like in the first figure, which was what? 30. So that means what we're going to cube is supposed to be 280. Okay, because it is just like this 60. So it's supposed to be my B, which is 80, my H, which is what? 280. So B is 80 times 280 cube divided by 12, as you can see here. Okay, then multiply with the area, 80 times 280. Then now the question comes, how do I get this R2? 140 minus 96, how did I get it? So here is what you have. The second figure is the web. The centroid of this, the centroid of the web only, if you consider only the web, it's at half of 280, which is 140. I believe you have got that. Now, that is why I have here what? 140. But the question is, where is this 96 coming from? Okay. Yes. Now, you realize that from here up to here is what? Is 156, right? So 156, what about from here up to here? This distance. Okay. This is 156 minus what? Minus 60, because from here to here is 60. So you remain with what? 96. Get it? So if that is 96 now, from here to here is 96. But from here to here is what? Is 140. Half of that is 140. It means that the distance between these two centroids is what I want. You get it? This distance is what I'm calling what? R2. Okay. Well, so that's why I have 140 minus 96 and you square it. Then you do the same for figure 3. That is the bottom flange. Area is 100 times 60, then cube it, plus area, which is what? B is 100, which is this, then cube this one, 60. Then multiply with the area, which is this times this, then multiply with what? Again, the value of R3. Now, the centroid of this is 30. From the bottom, from here to here is 30, right? So if that is 30, what about the overall centroid? Is at what? Distance of 244 from the bottom, right? So 244 minus this 30, then you cube it. That's our R3. So well, when you press this, everything here, you add it up, you're coming to what? To this value of 7.58 times 10 raised to power 8. So that's what we're calling the I. Now since we have got the I, unlike in the previous question that we did, here, for us to find the modulus or sectional modulus, okay, Z, section modulus Z is obtained by I divided by Y. Okay, so let me show you how to do it. Here we go. Z from the top, I divided by Y. So you realize that the value of I remains the same, but Y from the top is 156. Okay, so you get this answer, cube. Then Z from the bottom is I divided by Y. So I is the same, divided by Y from the bottom, okay, is 244. So you get this. Up to this point, I believe that it's well explained and you've got. Now, we are going to utilize all these things that we were finding to help us solve our question completely and amicably. So let's proceed and find what we call the dead load. So the dead load is obtained from the area of the whole section, which is the area of the what? Flange, upper flange, web, then area of the web, then area of the bottom flange. So this is the total area times the density. It gives us what we call the what? The dead load. Why is it divided by 10 to power 6? Is just to convert it to kilonewton per meter. Then the live load is given in the question as 2 kilonewton per meter. Now we have to obtain what is the moment due to dead load. The moment due to dead load is given by, if I call it Q times L square divided by what? 8. So that is Q is 1.12 times L squared, which is 8, the span is 8 square, and divide by 8. You get this answer, right? Then the dead load, if the dead load is W for instance, so it becomes W, which is 2 L squared divided by 8 also. So this is what we have obtained as 16 kilonewton meter. The unit is important. Now let us now go as far as calculating the stresses that this I section beam will experience. The direct stress, starting from direct stresses, at the top, it is P divided by A. Now, P is given, prestressing force is given as 100 kilonewton. So, to change it to Newton, I multiplied by 10 to power 3 and divide by the total area of the overall I section beam. So, I believe you know this. The answer is coming from, to be, 2.16 Newton per millimeter square. Just the same as that at the bottom, it is the same answer. So, 2.16. The first thing of the stress is done. Now, let us get another stress, and this is the bending stress due to prestressing force. Bending stress due to prestressing force here. So, due to prestressing force, we learned that the formula is given by the expression PE divided by Z. Now, since we are starting from the top, so P is 100 kilonewton, that's 100 times 10 to the power 3 Newton, times eccentricity, whether from the top or bottom, eccentricity is same because the force is acting at 100 kilonewton. So you need to know what's the distance from where the force is acting up to the centroid. Why? Now, eccentricity is 194. So from the top, the only thing that is changing is 485, which is the Z value. Top, the Z value is different. Bottom, the Z value is different. So we're getting negative 4 Newton per millimeter square. You ask me, how did you get this negative? When we get to the stress distribution diagram, I'll show you why it is negative and why it is drawn like that. Okay. So let's proceed and get it at the bottom. At the bottom, the formula is PE divided by Z at the bottom. So our P remains the same, our E remains the same. Then the Z at the bottom is 310 times 10 to the power 4. The answer is coming to positive 6.25 in Newton per mm square. We're done with bending stress due to prestressing force. Let us now get the stresses due to the loads which are imposed, the dead load and live loads. So here we go. At top, the formula is first of all given by moment due to live load. We're starting with live load. Moment due to live load divided by what? The section modulus, which is Z. So from the top. So moment due to live load at the top. The moment due to live load we found to be 16. So 16 times 10 raised to power 6. This is to convert it to Newton millimeter. Okay. Then divided by Z at the what? At the top. You get positive 3.3 in Newton per mm square. Then at the bottom, it is moment due to live load, which is still the same 16, divided by Z at the bottom, which is 310 times 10 to the power 4. The answer is coming to negative 5.15 Newton per mm square. So we are done with getting the stresses due to what? Due to the live loads. Let us also get the one due to what? Dead load. Well, so the stresses due to dead loads. You realize that at the top, the dead load, the moment due to dead load, first of all, we calculated it and we found it was 8.96 times 10 raised to power 6 is just to convert it to Newton millimeter. So divided by Z at the top, which is 485 times 10 raised to power 4. The answer is coming to 1.86 Newton per millimeter square. Then at the bottom, moment due to, this is supposed to be dead load, sorry. Moment due to dead load, divided by Z at the bottom. So this is 8.96 times 10 raised to power 6, divided by Z at the bottom. So the answer is coming to negative 2.89 Newton per mm square. These signs have come because of the way you have to draw a stress distribution. Now to answer our question, let's see how we can draw the stress distribution and how we can find the resultant. Remember, our major goals remains finding the resultants under different load conditions. So the first part is you have to find the resultant at both top and bottom when you have only the self weight plus the prestressed force. Now the stresses coming as a result of what? Of prestressing. The diagrams that you will obtain in that case becomes only this. Okay. This is due to prestressing, right? Then the one that is coming as a result of self weight, that's the dead load, is this. Okay. Remember, our first question is talking of that. So we need to get due to prestressed plus self-weight. Okay, so remember, this is direct stress and this is due to prestressed force and this is due to dead load. The resultant, now according to these signs, this is 2.16 minus 4 plus 1.86. You will come to what? To 0.02. Then at the bottom, this is 2.16 plus 6.25, then minus 2.89. You'll find the resultant is 5.52. Now, I believe you have understood how we have found the resultant at both top and bottom. Now, let us also find for the second case. The second case is when we add, in addition to that, prestress and self-weight, we add again live load. So, the diagram is this. This is due to the direct stress. This is due to the prestressing force. And this diagram is due to the what? The dead load. And this one is due to the live loads. So, what could be the resultant? Get it at the bottom. So, sum up this, you get this. Okay. Then, the upper one, you do the same. You're getting 3.32. And the units remains Newton per millimeter square because they are all stresses. I believe you have understood how this problem has been solved carefully. Thank you so much for watching this video till the end. If you like the video, if it's helpful, so please like, share, comment, and then above all, still subscribe to my channel so that you always get informed if the new video is uploaded. Thank you.